Welcome to another GCBASIC demonstration. This one is not specific to a chip, it's actually just a generic approach on how to do I2C Discovery. So, this is all around how you get I2C operating. But sometimes it doesn't work. I'll try and explain why it doesn't work, and we're going to go through a process of discovery. So here we go. Like and subscribe. Always do that. Watch the video all the way through. Shows a couple of Q24 chips. Not specific to that at all. Not even. It's just generic approach. Okay. So typically, I would be discussing discovery like video 11 in a whole series. So this is sort of based on video 11, but we're going to go a bit deeper just into the discovery process. So GCBASIC, open source compiler for PICs and AVRs, and it supports software and hardware I2C, and that's quite important. It supports both. I had a conversation this morning, and Kevin said, "I just use software. Don't even bother with the hardware because it works well." So let's have a go. See what happens. So I'm making some assumptions that you've got your software installed, you've got programmer, got PIC attached, and you've got a switch, but it's not it's connected up. It's not mandatory. But it is mandatory that you have a USB TTL converter. We'll have a look at that. And you've got some GLCD devices. Let me show you what I've got. Desk cam. Got a board, old 2010 board. I put a K42 chip in here, and I've got some devices in here, and we're going to pretend that we don't know what they are. That's fine. I've got a PIC kit 2 connected up. I've got USB TTL converter. Was connected, not anymore. Connected up, and I've got that connected up to a serial outline here and a ground line on the back of that rail. So basically, shortly, any serial connection stuff will just come out of here into my USB TTL converter, and then we can see it on the screen. It just makes it easier. And we'll look at that to sort of justify that. Okay, so I2C is a bidirectional communication protocol, and it uses open collectors and open drain lines that are pulled up with resistors. There are two lines, data line or serial data line called the SDA, and the clock line, serial clock line. And they both need to have pull-up resistors. Typical voltages are 3.3 or 5, and I'm talking here about what is not I3 squared, but I2 squared. And so those voltages, I'm using 5 volts. Hardware, set up a prototype board, and we put a pen up. Seen that? I told you I'm doing 5 volts. I've got a programmer. I'm using a PIC kit 2. I've got some LEDs, but what is important is the pull-up resistors. You can have a switch on there, and that just helps you with what we're doing. And an I2C device and circuit. That's sort of what we're going to be doing. Now, I've got hooked up the data SDA to port C4 and C3 for the clock. I've also got, and it should be very clear here, I've also got a transmit on here. There are other LEDs and other things, but those are the three things. It's C7, C4 for data, and C3 for clock. We need those in our brain because otherwise it won't work. Okay, typical device might be GLCD. We've got lots of devices on here. I connect that up from the SDA connector on the GLCD device to my chip down here somewhere, and the same with the clock line. But what is important, you have these two pull-up resistors to voltage. Now, you could use the internal pull-ups, just if you want to add some more complexity to the problem, okay? If you want to get this right first go, just use external pull-ups, and then when you've got it proven that it works, then move to the internals. It might take a little bit more thinking, but it does make it a lot easier. So I've got external pull-up resistors, and that means that we'll have simplified code. So what we're going to see, not in any detail this sequence, but we're going to send out a start signal which toggles the lines, send some data, an address, and then some data, and it will stop. And that protocol is all within what we'll call the discovery program that we're going to be using. So it sends out a start signal by dropping the line. It transitions the line from high to low, sends out an address with data toggling, sends out some data, and then it stops by transitioning the line from low back to high. And without that control, the microcontroller will not work. Hence, you have to have the pull-up resistors. So what we're going to see is this. We're going to see a display that, forget that hardware because we're going to be seeing software as well. We're going to see a display like that, and it says 79 hex and 78 hex, 79 hex. That's where there's an address sitting there. It tells us there's a device there. It also tells us the bus is working because it wouldn't have seen it otherwise. And it tells us that the communication protocol is working well and the underlying libraries are working well. So without that, no point in proceeding. So what we're going to do, we're going to create a program using existing resources, and we're going to use software I2C, and then we'll look at hardware. But we're going to start, always start with software. So what I've got is GC code installed, operating, and I'm going to open up a folder. And in that folder, we'll find a file as our resource. So I'm just going to zoom in for you so you can see it. I'll just move the screen slightly. File, open a folder. I'm going to open up a folder, and it's going to be on my C drive, and it actually might be the same for you. C drive, GC Studio, GCBASIC, demos, I2C Solutions, / I2C Discovery. Now, let's recap. In the demos folder, I2C Solutions, I2C Discovery. I will then zoom out so you can see me, press the select folder, and it selects the folder. And what it's done, it's loaded in all the files in that folder. Now, I don't want to, you won't get that message, I will get that message. So Control B opens up the long list. I was doing a search earlier on. And if you click on the top icon there called Explorer, it will open up and show you all the files in there. And there's lots of them. Recommend, as we're going to create a new one, just take a really old one. An old one. Let's start with this one here. 16F 1939. Take it. Control B, shut that window down. Okay, let's find out what chip we've got. Well, I've got a 18F 20. Oh, it's not. It's a 47K42. Well, let me just check that. I'm just going to load up PitKit 2 just to check that. Yep, there it is there. I can see it on the screen. That's fine. So I leave all this. This is all the software stuff we need. We need data in, blah, blah, blah. We need to configure the serial port for us. So I'm just going to delete all that. Okay, and go __ US. Oh, no, that was wrong. USR setup, and it just puts it in at 9.6. That's fine. That's what I want. The data lines here look correct. That's port sealer, and this is zoom in. C4, C3, that looks correct. Looks all right, actually. But what about this serial? I'm going to need some PPS for this because this is a PPS chip. So I'm just going to put my cursor there. PPS running? We'll find out. Function key F4, PPS tool. Get the list of files. There's the K42 already selected. I need to transmit. You can't see it on the screen. I've just selected it by going click. You can see it at the top here. And I want that on C7. I said that's on C7. Copy. Oh, no, sorry. I'm going to add it in first, aren't I? Copy. Press OK. And then back into my program. Control V. Now, as a general rule, my advice, not general rule, do this. Set the chip to 4 megahertz. You don't want to bash the bus when you're doing this. Okay, so just try it slowly. Okay, so 4 to start with, and then increase it if it works. Then you've got a good configuration. Okay, so we've done that. What have we done? We've changed the chips and the frequency. We've added the PPS because we need it, and the rest of it we didn't change apart from just clarifying this USR setup. Seems good. Open up a terminal by pushing function key F9, and here it is. I'm just going to rescan it and connect. I've now connected my terminal through the USB TTL to my PIC. Function key F5 to program. You can't see that, but it's doing it on the screen at the moment. It's just programming it. Look at the terminal. Well, that don't look right. That means we've got an address on every line, which is totally wrong. That doesn't look right at all. Why would it have done that? I'm just going to power cycle the chip to make sure I haven't got some sort of PPS hanging around inside it. That means the bus is high. It means it's not working because it didn't report back what we're looking for. Anything with question marks means it's not working. Sorry, cough. Anything like that means the bus isn't working properly. What have I done wrong? Have I got the ports right? Data's on 3. Data's on 4, sorry. Clock's on there. For those playing along at home, I have used a hardware discovery. I'm just going to restart. Okay, so what a clown. I want a software one to start with. I'll take a 690, software 690, that would do. Look. Okay, let's change my chip. 18F47K42, comma 4. Same rules as before. Zoom in for you as I edit this. Leave the setup here, that's correct. I'm going to have to change the port here. C.4, C.3. Look, you know, I just like I'm not tidy. USR. No, we've already got the PPS over here, so I can take. Oh yeah, Wally. Take a copy of that. Pop it in there. So what have I changed? I've changed the chip. I've changed added in the PPS. Changed my ports. Saved my file as (18F47K42). Enter. Function key F5. Out to the terminal. So my previous error, my previous effort was totally incorrect because I'd used the hardware. A bit of a mix there. Oh, look at that. Isn't that fantastic? So that tells me I've got a 9A address and 9B for a read, yep, 9A write and an A1 read. It works. So it's really important. I didn't change the body of the code. I just did the setup piece. So you can output all this stuff that's in here. I am not going to demonstrate that because we now know the bus is working. You can, wherever it says print screen, you can put it on there. I don't care how you do it. Now, we now know we have a software one working, but does it work at 64 megahertz? Function, put that up to 64 megahertz. And if it doesn't work, drop it down. It's because the bus is going too fast. Okay, if it works, it works. If it doesn't, just drop it down whilst we're doing this testing. Oh, it works fine. Okay. So always put it to 4 just to check everything's okay, and then up it. We now know that we have got The I2C bus is pulled up high. It must be because it's coming up and down low. We got addresses responding. Fantastic. File, save as. And we know the ports are correct, by the way. Software discovery. Change that to hardware. Hardware. It says it already exists. Oh, there's already one in there for hardware. Should I edit it or should I open it? I'm going to open it. Let me find it. I didn't know that, by the way. Software discovery is the one we're working on there. There's a K42 hardware discovery to terminal. That's this one here. Control B to get rid of all that. Control J to get rid of the bottom window. Oh, I've been in there before. So it says 47K42, 32 megahertz. That's fine. PPS, we've got to inspect the PPS because we haven't written this. PPS. Let's have a look at someone's done some fancy stuff in here, haven't they? So the clock's on 3. The data is on 4. Is it the right way around? I can't remember. Data's on 4. That's correct. Yes, that's fine. There's a lot of other settings required for hardware. Look, that's come from the data sheet. Some levels for the pins. Set it as an open drain. That has come from the data sheet. PPS is on RC6, not 7. That needs to be 7. Because what was it before that worked? RC7. It's right. This board is a 7. It's not me. You can actually do this. It's quite safe if you know what you're doing. I've just changed the PPS. Baud rate's 600. That's quite fast. 400 down there. That is quite fast. And that's the same. And then there's a dump here. Function key F5 to program it. Clear that down. That's the software one that you can see. It says software. And now it says hardware. We've now moved from software to hardware. It's not hard. The only difference is, the big difference in here is that you've got to set up the PPS correctly for the module itself. Now, depending on what module it is, you might have to set the clock and the data as an input or output. This is interesting. So it has to be an output. I will write up a note on this. Use an example like this and it just works. So what would I do if it didn't work? Well, if it didn't work, I would do the following. Let's go out to the camera. Go get one of these. You don't need an oscilloscope for this. This is how I did it, just a logic, cheapo. This is $3 or $4, right? Yeah, you can go and get yourself an oscilloscope. You can hear it. You can hear it, can you? Hopefully you can. That's the output there. Oh, stay quiet. This is my target IC. Over here, that's the EEPROM. Sounds good. That's the source chip. Bit quieter. Well, you can hear it moving. I mean, you can hear that that's working well. And here is the temperature sensor. Oh, we said it could be louder for you. Each time I can hear it. You can use an oscilloscope to do the same. You don't need a protocol analyzer, but that's using either. Now, here's a trick. I have just used hardware I2C. It's on the screen here. I'll just use this. Hardware is the hardware version. Watch this, look. When I go back over to the, I'll just close that file. If I go over to the software one and I program it, well, look what happens on the terminal. This is sort of important. So that's the software one. Oh wait, it worked. I am genuinely surprised. Some later microcontrollers do not retain their PPS settings. You must power cycle. And this has not been power cycled, so I'm surprised that works. But on some of them, it would have to be power cycled between a hardware software operation and a hardware I2C operation. So here we go. This screen is important. Don't even try accessing the I2C devices unless you see something like this on a screen somewhere that says I can see the addresses that you're looking for. As you can see on here, there's two. Let me just grab something else. I'm just going to do this live. Desk cam, do this live. I'm just going to unplug that. 1, 2, 1, 2. I have to take these 4 off of here. Look. Okay, that's SDA. I always use blue for the SDA. I always use yellow for that. The power goes on there. Power. That's it. What I'm doing, I'm actually attaching up another device. 5 volts in there. Ground in there. Got to try and remember. Where was the C? Hey, let's have a look. We'll just try. We're going to put that up there. C3, C4. That's what we got on the terminal. What we got on the terminal? Oh, we got no power. The power's come off. Look. We look at the terminal now, and we're going to Zen mode so you can see it. In the terminal here on the left, look, we're not finding that device. So I'm going to stand up, see if it's wired up correctly. Well, we know the bus is working. RC4. Clock's all still powered up. We have another device, 78 and 79, that's been added. I wouldn't even try accessing that GLCD without doing this test. There is no point. It's very, very hard. So with that, I am going to go back to my PowerPoint and call that a wrap. Doing the testing properly using software discovery is important. Enjoy.